Hi, this is Chris with Sanderson Test Prep, and in this chemistry video we're going to take a look at some of the most common conversions that we have to do in stoichiometry. So we'll look at examples of converting grams to moles, to molecules, to atoms, and let's go ahead and jump right into it. So the first example that we'll look at is this question here about how many moles are there in 88 grams of carbon dioxide. So whenever we are going to do a conversion when dealing with grams and moles, we're going to have to get molecular weight. And that's what you're going to get from the periodic table by looking at the atomic weight of each element. So for carbon, if we look at our periodic table, carbon has an atomic weight of 12 grams. And we're going to add to that the atomic weight of the two oxygens. That's why we're multiplying by 2 here. Each one's 16 grams. And so when we add that together, 12 plus 32, that'll give us 44. So we have 44 grams as the atomic weight of carbon dioxide. Now, in order to figure out how many moles that is, we're always going to start, when dealing with stoichiometry, with our given value. The given value here is 88 grams. So we're going to start with 88 grams of CO2, and then we're going to do our conversion. I like to write it out like this. I think it's a little bit faster. Many of you might be more familiar seeing something written out like this, where you write times and then the next conversion factor as a fraction and so forth. So you're welcome to write it out in any way, but just as a little shorthand for me, just setting it up like this is a little bit faster. So for this conversion, you always want to make sure that the units that you have cancel out, which means that down here, we know that we're looking to put grams of CO2. And so if you ever get stuck during a conversion on a stoichiometry problem, this is a great place to help put you on the right track, is just write down the units that you have from the previous given value in the denominator of what you're multiplying by. And then once you write that out, a lot of times it can help remind you, oh, okay, now I see where I need to go. So in this case, our molecular weight, 44 grams of CO2. Molecular weight comprises the amount of grams for 1 mole. And so that would be for 1 mole of CO2. And when we multiply and divide, 88 divided by 44 will give us 2. So in 88 grams of carbon dioxide, there will be 2 moles. So that comprises 2 moles of CO2. But what if we're asked to go a little bit further, right? Sometimes we don't just need moles. Sometimes we need molecules or perhaps atoms. So let's take a look at a couple of those examples, continuing off of this same foundation. So here it says how many molecules of carbon dioxide are there in 88 grams of CO2. So again, same given value that we started with before, but now we have to find molecules instead of moles. So we're going to set it up very similarly. Start with our 88 grams CO2. And first things first, we have to convert that into moles. So that's the conversion that we just did. 44 grams CO2 comprises 1 mole of CO2. And then we need one more conversion here. So we are going to introduce a number here called Avogadro's number. And that tells us how many molecules we have per mole. And that number is a constant value. It's 6.022 times 10 to the 23rd. So that's how many molecules we'll have. Sneak that in here so we don't run out of room too terribly much on this. And then now we do our calculation. So 88 divided by 44 is 2 times 6.022. That would be 12.044 times 10 to the 23rd molecules of CO2. Let me sneak that in just to make sure that it's correct. I'm going to zoom in for a second. Just put the CO2 over here so that we know what we're solving for. And then to convert this into proper scientific notation, since we have a number greater than 10 in front. So this number in front in scientific notation is called a mantissa. So if that's greater than 10, that means we have to move the decimal. And so here, for proper scientific notation, we move that decimal one place to the left. And if you make this number smaller, then that means you're going to make your exponent larger. So moved one space, which means I add 1 to the exponent, and I end up with 1.2044 times 10 to the 24th molecules of CO2. Now let's take a look at one more example in a case where we're asked to find atoms. So the last step in this whole conversion process is if we were asked to find atoms of oxygen, for example, in this same given value of the 88 grams of CO2. So we're going to go through the early parts of this conversion a little bit quickly here and then just discuss briefly how it changes with this last step. So starting with our same given value, of our 88 grams of CO2. And I do encourage you to get in good habit of actually writing out what that molecule is. A lot of times people want to shorthand it, and a lot of times you'll see that people just write like, oh, 88, 44, 1 mole, 2, 3, and the more that you get in a habit of using shorthand early on, the more trouble you'll run into later when you get to more complex examples where you're doing multiple conversions in the same complex problem. So here, 88 grams of CO2, we use our molecular weight to convert that into moles. That would be 1 mole of CO2. Then we convert the moles of CO2 into the molecules of CO2, as we saw above. So this would be 6.022 times 10 to the 23rd. And for this one, just because it's really long, I wrote that a little messy. Let me clean this up a tiny bit for you. So this one, I'll just write molecules, and I'll just put the C there so we know it's not moles, so that we know it's molecules of CO2. And then our last step here, so now this is the added part of this conversion. And so here, 1 molecule of CO2 has a certain number of oxygens. How many atoms of oxygen are in there? And so that's where you're going to look at this subscript. So whatever that subscript is, that tells you how many oxygens you have in that individual molecule of CO2. So here we have 2 atoms of oxygen. And now we can multiply everything all together. So here we're going to have 88 divided by 44, which would be 2, and then times 6.022, so that would be 12.044, and then times 2 again, so that would be 24.088 times 10 to the 23rd atoms of oxygen. And for proper scientific notation, we'll do exactly what we did before. We move the decimal over one place to get 2.4088 times 10 to the 24th for our final. So those are a couple of the most common stoichiometric conversions that you'll be asked to do in chemistry. And if you have any questions, please feel free to reach out or check out our other videos. Thanks for watching.